Okay, thank you everyone for coming. I was asked to introduce Rowan on behalf of the UC Alumni Association, for which I sit on the Award and Recognition Committee. Rowan is an undergraduate alumnus from the UC, where he first started developing geoscience visualization software. He later became a Vanier Scholar and Killam Laureate at the UBC, where he finished his PhD. And in 2018, he received UC Alumni's first Early Career Achievement Arch Award for his leadership around visible geology, SIMPEG, and three-point science. So without further ado, introduce Rowan.
Yeah, thank you very much. I was asked to sort of give a talk without very many constraints, and so I have like a decade worth of stuff to talk about, I guess. I think the last FATS talk I gave was on visible geology, and that was 10 years ago. So that's that first icon, and that led sort of into an entrepreneurial side of things, starting a company around that called 3-Point Science, which was later acquired by Sequent, which has an office here in Calgary. And then I'll talk a tiny bit about some of my PhD work as well, which is called SIMPEG, that does simulation and parameter estimation in geophysics. So I guess I want to start with a bit of a story. And it was actually in this class that was my first structural geology class, where the instructor sort of got up in front of us and said, structural geology is hard because it involves 3D visualization. And some of you have that skill and some of you do not. So some of you will struggle and some of you will just get it. And so what was sort of frustrating was that he was right. And then there was this like bimodal distribution in the grades of the class of the people who sort of just had that 3D visualization skill and could take those concepts and visualize them. And so they were the ones who just got it, and then there were sort of these other people who had these ideas, but they couldn't quite get them. And so that's because there's these sort of abstract concepts, maps, stereo nets, that really are 3D visual objects. And we have tools these days with computers to actually see that stuff. And so that's some of the work that I did as an undergrad here back in 2009, working with Leslie Reed and Adam Pidlasecki on creating some tools for visualizing in sort of like very basic concepts of bedding, folding, dikes, superposition of those sort of geologic events. And so that was a tool that I introduced into the Geology 201 class with Leslie Reed, and I sort of got some uptake there. I took it to AGU, and it won some awards. I wrote a website for it. I sort of like tried to get it out into the world. I even made a 63-page PDF help document. So at the end of the day, after like 2 or 3 works of trying to evangelize this software and get it out onto the world, about 5 people outside of the University of Calgary actually used it, which to me was like really frustrating. And so it came back to me, and I sort of was thinking about how approachable it was and how accessible it was. And that's when I sort of turned to the web. And so that's where visiblegeology.com came in. And so I was using some new web technologies, WebGL and stuff like that, to actually do this plugin free in the browser, so you can just go to a website and actually start modeling some geology. And so it's a pretty approachable interface. So you just get sort of a blinking start here button. Who's actually used visible geology? Okay, I should have cut this part of your presentation down. So you sort of get beds. You can grab tilting events, you can see that. You can add folds, unconformities, dikes, faulting events, more folds, until you get something pretty complicated. And then you can put topography on it. You can change out the topography. You can see what happens. You can take a cross-section through there. And this is like the types of problems that we would get in Geology 201 is, what is the geologic history here? And so that's sort of taking this problem and thinking in the inverse direction. So unravel everything and what sort of process evolved to actually get to this geology. And so what visible geology allows you to do is work in the forward sense. So you can ask what-if questions, play around with sort of the order of these things, and experiment, which is a really cool thing. And so this is something that I've heard from students, that it's a much more approachable way to look at sort of these geologic events and work with them, and sort of make that concept more approachable and accessible. And so this is the difference when you put it on the web, I think. So this is the number of users as of this morning who have actually used visible geology, and I think there's almost 1 million. There's like 895,000 geologic models made using the tool, so that's like cool, I guess. And I think the other thing is, instead of making PDFs this time, other people made the help documentation, which was even better, and so this is a page in Spanish, sort of explaining how to use the tool. So that's something I learned from that. It was actually use the web. And so this, when I put the tool out there as well, it sort of got picked up in a number of spaces. So in the publishing industry and sort of education, but also in the oil and gas industry. Because it turns out that the oil and gas industry goes through basically all of undergrad again in 6 months, just sort of focused on their problem. And so they have a lot of money that they invest in training in oil and gas. And so it was sort of a cool intersection of fields working in the education space as well as in the corporate space, but people were interested in those same problems, which is sort of the technical communication side of things. So I started a company with Adam Pidlasecki, who was a prof here, and that was back in 2013. And some of the things that we first went after was sort of gamifying and creating concepts around visible geology, where you can actually sort of have different interfaces to these same sorts of tools. And we worked with the University of Calgary, got some grants to actually get these into the Gallagher Library and put some studies around them. So this is a study with apparent dip, so getting someone to slide the sort of a slider to sort of pick the true dip direction of a bed and seeing that intersect with topography. And so that's leads from concepts such as the rule of V's in geology of intersecting bedding with topography. And so behind the scenes of that, we were collecting analytics as well of sort of how people were using that, which was sort of interesting to see people struggling and sort of just exploring everything versus actually hitting it for the first time. And we did a lot of other exploration at 3 Point Science about sort of interactive visualizations, dynamic documents of sort of having it all linked up to the text. We did some physics modeling through web browsers as well as earthquake modeling using real scientific data. So that was a lot of exploration that we did. We were funded primarily through the oil and gas industry, doing training there. And the crash in sort of 2015 meant that we had to really get back to our roots about sort of what we actually wanted to do. And that was around the technical communication space. And what the sort of problem that we were trying to solve there was there's all of these scientists out there, geoscientists especially, collecting data, analyzing that data, creating models from that, and using all sorts of tools to do that, whether they be sort of proprietary industry tools or sort of academic research tools as well. And what we saw again and again is the way that people show other people is through static media, through PowerPoint presentations or PDFs. And so you're showing people, you're having a conversation, and you're making decisions on that, but that pipeline of information is a really, it's compressed, and it's not a very good way to sort of communicate some of these inherently 3D and interactive ideas. And so again, people are sort of getting lost here, and ideas are bouncing off them. And so what we were trying to attack was trying to make that a lot more interactive so that you could show people, have a conversation, and make a decision. one of the case studies that we did was at the University of British Columbia around a diamond mine exploration project up in the Northwest Territories. And so this was a whole bunch of geoscientists, geophysicists, geologists, and geochemists getting together and getting all of their data in one place so that you could actually explore it together. And we, at 3 Point, so multiple geoscientific methods. So this is like gravity, gravity and magnetics run from airborne surveys over the mine, as well as direct current resistivity geophysical methods, as well as the geochemistry and geologic interpretation. And so all of these are coming together to try and inform the subsurface model that is there. And what sort of 3 Point did at this side of things was try and run this in a much more interactive way. So everybody had iPads and like drawing on the screen and having that show up at the front so that we could actually capture some of those decisions and have an interactive conversation about the data that was there. And so the software that we were putting behind this was allowing it to be like shown to lots of people to actually make that conversation a little bit more interactive so that you could explore on your own and capturing some of the notes that people were making. And I'll show a bit of a demo of where that software has got to in a second. One of the people there was sort of a sponsor from Leapfrog. And he was quite interested in what we were doing. Leapfrog is a geologic modeling software primarily used in the mining industry. And so what was a very long and very stressful time ended up we got acquired by Sequent, which is the maker of that Leapfrog software. And I want to show you sort of a little bit about where we've gotten to since then, which is kind of cool. So I'll just show a bit of an interactive demo here. So this is San Francisco Bay, and this is actually pulling from a study that Adam Podlasecki did, and it was sort of a joint study between the University of Calgary and Stanford University. And so there's about $10 billion worth of agriculture in this area, in the Salinas Valley, and it's like within 200 meters of the sea. And so all of the irrigation that they're pumping out has problems with sort of pulling in seawater into the aquifers there. And so this, the study that Adam was helping run was one of the largest direct current resistivity surveys done to actually try and show that saltwater intrusion. And so this is the entire bay, and these are the direct current resistivity sections there, with the red being salty and the blue being not salty. So you can see sort of a lot of interesting features here, like pumping wells, actually pulling that water in. But this is sort of the first time that like a picture was actually shown of the entire bay. And this is something that is spanning lots of different political boundaries. And so it's showing all of that together so that you can actually see the saltwater intrusion is a pretty powerful thing. And so this this tool is called LFU, and this is what I'm sort of currently working on at Sequent. Cool. Okay, so I want to like switch gears a little bit and talk about my PhD, and then bring it back together and maybe have some questions. So my PhD was at the University of British Columbia, and this is a zoomed-in region of some of the work actually that I started with Adam Podlasecki here. So this is again the Salinas Valley that has that large amount of agriculture in it, and you can see here that it's about 200 meters from the beach, where you suddenly have strawberry fields. And so there's a lot of irrigation in here that's pulling in that salt water, And one of the practices that people are experimenting with is called managed aquifer recharge, and this is a pond where they capture water and then put that back into the aquifers. And so California gets a lot of water in the winter, but sort of all at once, so it runs off right away instead of recharging. And so the idea of this pond is to capture that water and infiltrate it back into the aquifer so that you can capture some of it and store it there. And so the scientific questions here are sort of where does that water go and how do we sort of optimize this process so that we can store as much water in there. And what that leads to is an interdisciplinary question where you have hydrogeology working with geologists and geophysicists so that you can actually image where that water goes over time. Sort of in behind those different fields are different methods. And so if you look under the covers of this, you have all sorts of physics describing how this sort of fits together. So you have Darcy's law in hydrogeology, you have Richard's equation for describing vadose-zone fluid flow. In geophysics, you have direct current resistivity, electromagnetic methods, magnetotellurics, potential fields like gravity and magnetics. And then in geology, you're interpreting results as well as interpolating in fancy ways. This is a radial basis function, which is the sort of fancy interpolation algorithm behind a lot of geologic modeling software. And so in this, you are collecting all of this data across multiple of these fields, and you're creating multiple models. And sort of the state of the science is how are you actually combining these models to get a better picture of the subsurface, and whether that's qualitative or quantitative. And so that's sort of how this is going about. And so my PhD was sort of looking at the interaction between Richard's equation and direct current resistivity. And so that's where I'll sort of focus. And so if we zoom in there, I'll just sort of go over sort of how these are conceptually tied together. And so on the left-hand side, we have Richard's equation, which is describing how fluid flows on the subsurface. So if you have an infiltration front, rain on the subsurface, that infiltration front is going through the subsurface and it's changing the saturation. And how and where it flows is dependent on the physical properties of the subsurface, so those hydrologic properties of hydraulic conductivity. And it's a bit more complicated in vadose-zone flow because that's actually a function of the pressure. But if we jump over to the geophysics side of things, that sort of same process is happening here. You're hooking up a battery to the ground, and where the current is flowing is dependent on the physical properties of electrical conductivity in this case. And how these two methods are connected is through that electrical conductivity. So you can imagine wet sand is much more electrically conductive than dry sand. And how that sort of saturation is mapped between those is through Archie's equation. So that's an empirical equation. And so this is like a complicated way of describing these two things can be linked together. And so the idea here, when using geophysics to sort of image what the hydraulic properties are, is that you hook up a battery to the ground, collect all sorts of potential differences. That is dependent on the electrical conductivity, which is mapped through to the saturation, which is then mapped through to the hydrologic model. Cool. So that's sort of where my sort of PhD was, and there were a number of sort of intricacies there. This is changing when you're looking at Richard's equation just in sort of the hydrogeology side of things. You're collecting data that's a lot sparser through time, and so the model that you could infer about the subsurface is less constrained. And so when you start collecting much more data, so in the example that we did in California, this was every 18 minutes over a year was the amount of data that we were collecting. And so you could get a lot more information about that subsurface. But this was sort of not from the numerical side of things, much less sort of driven from the hydro side. And so that going from those sparse data to sort of a dense estimate of data everywhere changes the inverse model that you're doing. So I don't know if people are familiar with PEST, but that's a software that people often use to sort of do parameter estimation by driving these Ford models. And that just sort of doesn't work quite as well. And so if you used PEST to do this problem for sort of half a billion model parameters, that would take about 8.5 years of computational time, which is a lot. If you do it sort of with the approach that we were suggesting, it took about 34 hours. So a big difference, but again, this is using some of the numerical model methods that are known in a lot of other disciplines and sort of applying it to this new problem. And then you can also do a lot better in terms of memory if you do it in an implicit sense. Cool. Okay. So that was sort of the one of the technical parts of my PhD, and trying to actually allow me to tackle that problem. But as soon as I got over that sort of technical hurdle, it gets into sort of the conceptual hurdle of there are so many questions here about how you actually connect these together, and it's also a lot of interdisciplinary questions. So this was one of the papers that I read early on in my thesis. And so people had gone through and done sort of single strands of making a lot of assumptions of how to connect these two problems together in sort of 1D or 2D. And what they found was that this couple inversion improved parameter estimation, and it has direct advantages. And one of the pieces there was it forced the hydrologists and the geophysicists to formulate this consistent framework so that they could actually work together. And that's what I was sort of talking to before, is that you have to bring the methods from geophysics over to the hydrogeology side and actually fuse them together. But it also was the primary limit to the routine implementation of these types of inversions, because it was really hard. And so by really hard, it means that you get a PhD at the end of it. And so each one of those barriers between those methods is a PhD-sized barrier. That's another way to look at this, is actually combining these things takes a lot of work. And so the way that I was approaching this was trying to break down those barriers between the different disciplines and trying to formulate this computational framework that made it sort of much easier to join these things up. And so the idea there is that you could pick data from different methods and actually combine them into a model that you could maybe do joint inversion on or coupled inversion and connect it to other disciplines. And so computational science framework. It's sort of a set of standards and components that you write. So this is where sort of the computer science side was really coming into my PhD. And the framework allows multiple researchers to actually work together. And that is on these sort of components that work with other components inside of the framework. And what that means is that one researcher in that discipline doesn't have to know everything about the discipline in order to actually advance their work. So they can rely on other people to actually advance their work for them or with them. And so that's sort of the approach that I took, was to try and break this down in a consistent way, to define those components and the interfaces between those components such that people could actually work together. So this is the framework that we came up with. I'll go through it briefly just to give you a very brief flavor of it. You need to simulate on something, so you need a mesh. We used a lot of finite volume techniques in our side of things, in 1D, 2D, and 3D, refining towards areas of interest or aligning to geologic layers. Once you do that, you need to take your physical equation, turn it into code, and then turn it into an image or a picture. And so that's sort of where our physics drivers were, and so we have had quite a lot of those. And then if you look at sort of the simulation, going from that physical model into the data that you get out of it, you get a model coming in, which is the physical properties. You need to go through some physical equations to generate fields everywhere, and then sample those fields at receiver locations to actually get some data. And so that's what's happening in the hydrogeology side of things as well as the geophysics side of things. What's sort of special about this side of things is that we need to do the inverse side of things. So it's the forward problem is going from the model to the data. The inverse problem is going from the data to the model, and that involves a whole lot of optimization. And so that means you need to form an optimization problem, and you need to say how your data is related to your predictive data, and then how you inject knowledge into that system through regularization. And then the inverse problem is sort of the step above optimization, where you actually are tweaking all of the knobs to get something geologically reasonable out, instead of sort of just fitting a math equation. And so this is where people are going in and creating all sorts of algorithms, but they're doing it in sort of a non-standardized way throughout the entire geoscientific discipline. And so under the hood of this, what this actually is a whole lot of code. So there's so far 19 contributors over the last 6 years, and we've sort of thrown and tried to do as many geophysical problems, with the exception of sort of seismic geophysics, and just a lot of code written, so 250,000 lines of code, but also trying to simplify that and create structure in there. And so that structure is that framework that I was talking about. And when you do that, you actually make it accessible. And so you can interact with that at sort of a much higher level. And so then we can talk about these pictures and these components, and we can import them into a computational environment and have sort of tab completion on saying, I want to create a data misfit. Well, these are the data misfits that the community has written. And what that allows is a whole lot of people to build on that work. And so that sort of extensibility of those ideas, once you organize and make it accessible, you can actually make it extensible to other people's disciplines. So a whole bunch of people have been taking these and actually building upon it. So this sort of statement was the same statement that sort of got to me in the structural geology class, of it being the primary limit to the routine implementation of coupled inversions is because we don't have those standardized components and interfaces between them. We can't actually make progress as scientists to actually like put them together in novel ways. And the reason that was the case is because it requires this uncommon level of collaboration during the scientific analysis. And so what I was trying to do with the application of a framework here was to actually make that uncommon much more common. And that's because all of the sort of future geoscience problems are much bigger than any one domain. Cool. So this is some of the stuff, sort of the approach that I've been taking through all of these stories, is trying to make these concepts approachable and accessible and extensible. And so in the visible geology side of things, going from sort of that static picture that might be an abstraction through a map or a stereo net to actually making it interactive or an animation, and then making it extensible means asking those sort of what-if questions, creating your own geologic model so that you can actually extend what other people have made by assembling the components together to make something that's your own. And on sort of the geophysics side of things, like Maxwell's equations are not that approachable because you don't actually get an image out of that equation. And so if instead you can put slider bars on physics, then you can actually make that much more accessible and approachable to undergraduate students and actually have them running simulations in a class. And then taking sort of the under the hood side of things and trying to actually break that down into the components and how they actually fit together is where the extensibility comes in. And so that's something I sort of stepped away from that community, but it has evolved, the SimPeg community, and is going places, I suppose, which is fun. So this is, yeah, just going back to that bimodal distribution of sort of the root of my frustrations is, like, a lot of times this is because people don't have the right tools to use, and the concepts therefore aren't approachable, accessible, or extensible to them. And so what I have tried to do over the past few years is to actually provide those tools to actually raise people's game. So people saying that it's the greatest tool they've ever seen. And I like putting that quote up on the screen. And so that's sort of my goal there. And then in the SimPeg side of things, really speaking to the extensibility piece, speeding up the initial learning process of geophysics in general, and sort of how you're putting these pieces together to approach problems. And that means because you don't have to do all of it yourself or all of it at once yourself, you can instead do small pieces that pull on a whole lot of other things and tackle new and harder problems. So that's a couple stories that I have. I don't really have too many other conclusions other than that, so I will say thank you.
So I'm really happy to be here to add our congratulations to the congratulations that Rowan already got for his Arch Award, which is a really special award that kind of went a little bit over the, I won't say under the radar screen, I'll say over the radar screen in the department. So we really wanted to acknowledge how proud we are of you. My first interaction with Rowan was when he left the program that I was teaching in, the undergraduate environmental sciences program. I have to say I was pretty disappointed. It's really clear that he belonged in the geophysics program and he really flourished there. And I want to tell you guys also that Rowan's part of a bigger UC family, which is the family that sits around the Sunday night dinner table at his house, his first house. His dad is a longtime computer science faculty member, and his mom just got her PhD about 5 years ago in environmental education with a specialty in ethno-ecology, which is a sense of place. And so I think it's kind of cool that Rowan studied geophysics and geoscience, and he specialized in computer science and in education. And his mom and dad are right now, I think, in the UK, right?
They're in Australia.
In Australia. Sorry, the other side of the world. I'm figuring out when to go see the moon on your mom's post. She's in Australia. I'm sure they would be there, and I'm sure also that Adam Pidlasecki would be here if he weren't at the headquarters of Sequent in New Zealand right now. And in my observation, like, really productive things come out of really unique relationships where there's great synergy and great collegial relationships. And I think it's fair to say that Adam and Rowan have shared that, even though they've kind of meandered around each other in what they've been doing, or, you know, not always worked together 24/7, but often. And so I remember Adam saying, when you were on one of your undergraduate summer positions, whether it was Pure or NSERC undergraduate student research board, wow, I'm really looking forward to working with this person. And so it's been really wonderful to watch what became of what I think started as your undergraduate thesis. Yeah. So we always like to see our alumni succeed, and I think success can take many different forms, but it's really so clear and so multifaceted, as in Rowan's case. So academic, I looked at your Google Scholar page. I think you have more publications in the last 2 years than I do. And some of them, I don't even understand the citation format of them. They're so new age. So academic success, entrepreneurial success, education success, and science. So it's been a really remarkable journey. And so you had your lecture where you understood that not everybody was going to get structural geology, maybe from somebody who was in this room. And then you gave a FATS talk here in 2010, and we're grateful you could come back in 2019 to see us again. So please join me in congratulating Rowan before we have a piece of cake.